Hi everyone, this tutorial is all about lenses. So we're going to be talking about two different shaped lenses in this tutorial, and in your textbook you can follow along pages 551 to 561. It's a lot of pages, but it includes a lab in there as well that we'll be doing in the classroom, so it's really not that much reading if you're following along with your textbook. So you can see two shapes on this slide, convex and concave, and you are familiar with those terms from our curved mirrors. Now the difference between a mirror, a curved mirror, and a lens is that a lens is completely transparent. So light is going to pass right through the lens. But due to its different shapes, and because it's a solid material, it is going to refract light. So light is going to bend as it passes through these lenses because it slows down. This is a solid medium, and so it's going to be slower than the speed of light in air. And so we do see refraction with lenses. And actually that's a really good thing because we can use these lenses to change the path of light for many, many different applications. There's probably more applications for lenses than there are any other optical device out there. So we'll continue by looking at these two shapes of lenses in particular. Now this is a converging lens, and you'll notice it is a convex lens. So we have this shape convex, meaning it's bending outward. Convex lenses are thicker in the middle of the lens and thinner towards the ends of the lenses. But they're also called converging lenses, and the reason is, you can see in this diagram, as light enters the lens, when it strikes the center of the lens, it bends and it comes out the other side at a point. So we call that the focal point. We saw those with our mirrors, but the focal point is on the other side of the lens because the light is passing right through. So this is F, our focal point. And all these parallel rays that are striking the lens are converging at a point, the F, focal point, and so this is called a converging lens. Now you have to be really careful to not get confused with the mirrors, because with our mirrors it was the concave curved mirror that converged light rays at F. It was the convex mirror that was a diverging mirror that sent light out in different directions. So in terms of converging and diverging, it's the opposite for the shapes of the lenses. A convex lens is a converging lens. Here's a diverging lens. So this is our concave lens. We were just looking at a convex lens, but this is a concave lens. It caves inward. It's thinner at the middle and wider at the ends. And this diagram is a little bit fuzzy, but you can see that these parallel light rays that are striking the lens are then heading out they're splitting up, they're heading out in different directions. So that's why it's referred to as a diverging lens. The light rays diverge on the other side of the lens. So now we're going to talk about the terminology used with converging lenses. And we see the same terminology used with diverging lenses as well. Some of this language is the same as what you saw with the mirrors. So we do have a principal axis, and the principal axis runs right through the center of our lens. It's a perpendicular line to what's called the vertical axis. So you see vertical axis right here, and it's an imaginary line that runs vertically down the center of the lens. And we have the principal axis at a right angle running straight through the center of that lens. So principal axis is the same as our mirrors. We also have F, so you can see F right here, and that was the same in our mirrors. With lenses, we have a focal point on each side of the mirror, however. So think about, why would we have a focal point on, oh sorry, I think I just said mirror, I meant lens. Why would we have a focal point on each side of the lens, whereas in the mirror we only had one focal point? So think about that for a second. Pause the video if you need to. So I hope you realize that we would have a focal point on each side of a lens because light can pass in either direction through a lens. So we need to have a focal point on each side of the lens. It's not like a mirror that's reflecting the light back in the same direction as the object. In that case, you would just have one focal point, unless it's a diverging mirror, and we know that the focal point is then behind the mirror. But with a lens, there's always two focal points, one on each side of the lens. We do have a way of designating which focal point the light rays are going to, though. And that's by using these terms, principal focus and secondary principal focus. So the principal focus is your focal point that is on the other side of the lens from where your object is. The secondary principal focus, or F prime, when you see this little like an apostrophe beside the F, that the word we use for that is prime. So this is called F prime. It is the secondary principal focus, and it's the other focal point, but it's always on the same side as your object, so we don't have light rays reflecting through that focal point. So we call that the secondary principal focus. And you can double the focal length in order to find 2F and 2F prime. So once you know the focal length, you just double that and put a mark on your principal axis, and that tells you where 2F is. The only other term that's new with lenses is this one right here, the optical center. So the optical center is right where your principal axis and your vertical axis intersect. So it's right here. That is O. Okay, the optical center. On our mirrors, we called it the vertex, and the reason we called it the vertex is because we didn't have a vertical axis with the curved mirrors, but we do have it with the lenses. So that's the terminology we'll be using, and I'd like you to be using when talking about lenses. Now here's the terminology associated with diverging lenses, and this diagram's not great, but I just wanted to point out that it's actually exactly the same as the converging lenses. We have a principal axis, we have a vertical axis that goes right down the center of the lens. This would be O right in here where those two lines intersect, and you can see that we have a principal focus right here, and we have a secondary principal focus, or F prime, right there. And we have 2F prime and 2F that are 2 focal lengths away from the lens. So now I'm going to go over how to draw ray diagrams for the converging lenses. And there's a set of rules. Just like with the curved mirrors, we had 4 rules. With these converging lenses, there are 3 rules. They're really easy to learn. The more you practice ray diagrams, the more this will just become like second nature for you, and you'll be able to whip off one of these diagrams very, very quickly. Again, you have to pay attention to your accuracy and your precision. That's very important. If you're not accurate, then your image isn't going to end up where you need it to be. We will again be classifying our image characteristics using the SALT characteristics, so size, attitude, location, and type. But you'll see that when we're classifying type, whether it's virtual or real, that's a little bit different than our mirrors. Okay, so let's start with the first rule. Number 1, a ray that is parallel to the principal axis is refracted through the principal focus. So here we have our principal focus, F, right here. This is the line that Rule 1 is showing. As a light ray goes parallel to the principal axis and strikes the middle of the lens, it refracts through the principal focus. So you will draw a parallel line to the vertical axis in the middle of the lens, and then a straight line from that point through F on the other side of the lens. That's Rule 1. Rule 2 states that a ray through the secondary principal focus, so that's the focal point that's on the same side of the lens as your object, will be refracted parallel to the principal axis. So this picture, this ray right here is showing rule number 2. We have a ray that is passing through F prime, the secondary principal focus. You draw that in a straight line until you hit the principal axis of the mirror right about there, and that ray is going to come out parallel. Okay, I can't draw straight lines on this app, so sorry about that, but that would be a straight parallel ray coming out the other side of the lens. And the third rule is really easy. You take your ruler, you line up the tip of your object with the optical center. So right here, that's O, the optical center. And a ray that passes through O continues in a straight path without being refracted. And where you see those 3 rays, if you follow those 3 rules, you're going to get 3 rays on the other side of the lens that are meeting up here. So this is where our images, the tip of my arrow for my image is going to be right here. And again, just like the mirrors, we always draw back to the principal axis, so we draw our arrow going back up. Now, if we were classifying the SALT characteristics, I would say, so for SALT, I would say, here's my image, and I'm comparing it back to my object. I would say it is the same size, It is inverted, however, it's upside down. It's located on the other side of the lens beyond f. And the type, this would be real. Now this is where it gets a bit confusing. With our mirrors, if our image ended up behind the mirror, we said it was a virtual image. That's true of mirrors. With lenses, remember this is light that is passing right through a transparent lens. So those light rays are actually meeting up. We didn't have to do anything to them. We didn't have to extend them anywhere. They're meeting up all on their own on the other side of the lens. So this is actually a real image right here. And finally, we'll go over the rules for ray diagrams for diverging mirrors. The rules are pretty much the same. The difference is because it is a diverging mirror, our focal point is actually on the same side of the mirror. I keep saying mirror, sorry, I'm getting them mixed up. On the same side of the lens as our object. And it's because the rays are spreading out on the other side of the lens, we have to use the focal point that's on the same side of the lens. So rule 1, a ray that is parallel to the principal axis is refracted as if it had come through the principal axis. So right here, we have this parallel ray. It strikes, so there would be a vertical axis here in the middle of the lens, and it refracts off in this direction, but we would just take our ruler and we would line it up back here with the principal focus, and that tells us where to draw that refracted ray that's heading off out into space. So that's the first rule. The second rule is that a ray that appears to pass through the secondary principal focus, so that's over here now, is refracted parallel to the principal axis. So you would take your ruler and you would line up the secondary principal axis. Now in this diagram that I took from Google Images, they called it F2. Your textbook uses F prime, so it would actually be F with that little apostrophe or little tick mark, F prime. So you would just take your ruler and you would line up the tip of this arrow with F prime on the other side. And wherever that hit, right there, that ray is going to come out parallel to the principal axis. And finally, the third rule, a ray through the optical center continues straight through on its path. So that's actually the same as we saw with the converging lenses. So here's our vertical axis right in the middle. And here's our number 3 ray, straight line through O, through the optical center, continues on in a straight line. And you guys can see that here's our rays. That was the first one we drew right there. Here's the second one, and here's the third one. And they're not meeting up, are they? They're not meeting up on their own on the back side of the lens. And so therefore, we know that a real image is not going to be produced for a diverging mirror. You're always going to have a virtual image. And it ends up being back here. If we continue to extend all of those, I should actually draw those as dashed lines. I messed that up. So dashed lines, they're virtual, and they meet right here. Here's our virtual image right there. So we get this smaller virtual image. It's located on the same side of the lens as our object. And it's upright. So this would be a lens that would make our object appear much smaller. So you can think about where you might have an application for that. And a hint at the bottom, like I just mentioned, the characteristics of the image. Diverging lenses always produce those same image characteristics no matter where you put the object. However, with those converging lenses, those convex lenses, where you place the object is going to determine the salt characteristics of your image. It will change. They won't always be the same. And so in class, you're going to be practicing drawing ray diagrams for converging lenses with objects in a multitude of places along that principal axis. And in the lab, we'll be using converging and diverging lenses, and you will be looking to see what kind of images you can produce with a candle at various locations along the optical bench. So I hope that helped you because we're going to be practicing these a lot in class over the next couple of days. If you would like any more information about lenses, you might want to check out the Khan Academy videos. There's a couple of really good ones, some on convex lenses, and I think there's one on diverging lenses as well. So you can see those at YouTube if you just type in Khan Academy lenses. And you can also go to khanacademy.org and search the physics titles in order to find those on lenses.